you can ask for help. You can ask for help and I'll come along. Well, good afternoon, everybody. It's a great honor to be here. I've been attending for some years in the audience, and it's a great honor to be here explaining things. As Roman was saying, well, we are a niche that, well, sometimes it seems that it's very far away, and it's closer than expected. You'll see why right now. And well, the main reason of being sponsors, well, last year we were sponsors too, and this year it is about finding people. We need even more people than the one we have, because we have a lot of work, and there are people that would be interested in this. So please come along. We have a booth outside, so you can send us an email, by Twitter, however you want it. So I'm Mario Pérez de la Blanca. I work at Airbus Defense and Space here in Madrid, in Getafe, at a department that is product security. What is product security? This is cybersecurity, but throughout the life cycle of the product, since the conception, the development stage, up to production and delivery to the customer. And that includes especially cyber. We are in 4 countries: Spain, England, or UK, sorry, Germany, and France. The most important group is here in Getafe. The largest group is here in Getafe. So why is the speech called like this? Because of 2 reasons. Because AFDX is a twin Ethernet technology, and it has a twin Ethernet connector. It doesn't have anything else, but, well, we can see the word twin, and there's an electronic musician that is called Richard David James, called AFDX Twin, and I'm a great fan of him, and I wanted to pay some tribute to him. So we started by presenting discography in an agenda. Well, this musician has many records. These are just some of them that are quite representative in time, and the ones that touches the agenda, well, we'll speak about the networks, the historical data of the playing networks, how have we come to where we are, what is IMA, Integrated Modular Avionics, and a little bit more focused on the AFDX, in order to know key things. Well, of course, there's a lot of literature, so we don't have to explain a lot about what AFDX is, but just to understand what we are talking about, especially today, we are going to put an example of a pressurization system in a cabin. This is something that is very well known by everybody, because we've watched movies and because we are users. And we will move to the 2 last chapters. We'll speak about first valid wins. We'll see what its motivation, but for you to know, the first valid package wins. And we'll end up by collapse. This will be the FLT mode. This is the flight mode. So before starting with our discography / agenda, I would like to show a video. is something very dangerous and can be fatal for everybody that is on board. There are three types of loss of pressure: slow, fast, or explosive. The reasons are that maybe it could be structural fail because of a bomb, of a weapon breach, or metal wear. And the way of solving it is to go down as soon as possible. This flight was in August 2005, and it was a flight between Cyprus and Prague, with a connection flight in Athens. The Boeing 737 hit a mountain 40 kilometers north of Athens. While they were approaching the airport, everybody died. The accident happened when, after taking off, as they were going up, a fail when establishing the pressurization made everybody pass out. So it was some kind of ghost flight that was only flying because of the autopilot. So when they were in Greece, it crashed against a hill because of the lack of fuel. Now we really want to take a plane, huh? So after this appetizer, and before getting into the nitty-gritty, so we're gonna get started with the agenda. What are aircraft draft networks? So now planes are flying technology and software platforms. Complexity has increased a lot, and it has evolved since the purely mechanic systems to what we have right today. The first thing we did was to come to federated systems. These are software systems over hardware platforms that are quite similar to what we have at almost every environment. And this gave, and still gives, the systems some autonomy. Every system has its own infrastructure, its own operational system, its own hardware. There's a replication of systems. If there are redundancy problems, that's fine. But it has a basic problem, and this is that many suppliers, when there are many suppliers, there are some maintenance issues. It needs a lot of authorizations, and that is really expensive and time-consuming. So the space, the weight, another very important parameter when flying, and the energy consumption, well, these three elements were not as optimal as we needed. This would be the federated system architecture, where we find at every single column, well, at the base of the column, we have the sensors and effectors, take into account that a plane is an industrial system, as for example a power plant or an electric plant. We have sensors and actuators. Over them we have our way in and way out, our processors, internal system, our software applications, everything to give a function. Everything is controlled by functions. It is highly qualified at safety level, and everything is at functional level. This is very good, but as I was telling you, it has overweight problems, wiring problems, and so on and so forth. So the evolution up to AFDX, it comes from ARINC 429. ARINC 429 started to be developed in 1977. It has reigned a lot since then. And as of today, it is the most common network because it's the one that has been implemented. We didn't have time for it to replace it. In fact, it exists with other networks. Well, basically, it is a unidirectional network or bus with a single transmitter, and up to 20 receivers, and it has a low data rates, and it's a point-to-point connection. So the point is that the cables are very heavy, and they have an important cost in terms of weight, and the transfer rate is not the most optimal one. In 1995, 22 years later, Boeing developed for its 777 a higher speed networking solution to improve or mitigate these problems. And it evolved to bidirectional bus with up to supporting data rates up to 2 megabytes per second. It reduced the weight, and it fixed some problems. But the necessary hardware was highly associated to Boeing industry, and it was quite expensive. So the cost was a burden to implement it at some places. At the same decade, at the end of the 90s, there was an attempt to define another framework with ARINC 664. There are many, and ARINC 664 defines a profiled IEEE 802.3, and this is what it tried to do. And they divided this into chapters. They called it pods, and it's based on regular Ethernet, the Ethernet that we're speaking about IP, about PCP transport protocol, something closer, but it has to be improved. The part number 7 is the one that was focused on deterministic networks and full duplex networks. And this would be the part that would be referred to as AFDX. It is ARINC 664 part 7. AFDX, it's avionics full duplex switched Ethernet, and it was initiated by Airbus to define a robust ADN for use in the A380. So just as a detail, it has a star topology with up to 24 N systems. Well, N system is an AFDX concept. That is that every system that is connected, well, you need a card. You need an AFDX, and you can connect to any device, to a switch. The switch is very important in this technology. We'll see many more things later on. And then the switches can be cascaded in order to become bigger. Sorry, I'm a little bit thirsty. A lot. Well, it's basically a deterministic network. It's very important. It has redundancy at the link. It has some guaranteed wide it has a guaranteed bandwidth that we didn't have in previous networks. And well, EMAC was released the same year, 2001, with this record. And this video, well, last year it was our 50th anniversary at Airbus in 2019. So there were some commercial flights and defense flights as a matter of commemoration. And this has been all mixed up with AFDX Twin music. Let me look for it. Here it is. So this happens when you use a computer that is not yours. Okay, so EMA. This is integrated modular avionics, and it was here to solve the problems that we've mentioned before. In order to offer sharing computing and communication resources between the various avionic functions. I don't know if you've seen that before, but anyway, I've talked about it. There are some apps. Behind the networks, behind technology, there are apps that are executing. There's another ARINC, that is ARINC 653, that's in charge of developing a standard API that is called Apex for the operating systems that are, well, mainly on real time. And this is a standard way of executing applications. It defines the interface requirements and the list of services which allow the application software to control the scheduling, communication, and status information of its internal processing elements. This is an EMA system architecture, and as you can see on the lower layer we have sensor and effectors. This won't change, but they share many in and out modules. It doesn't have to be AFDX, but in this case AFDX makes its work. And depending on the type of function, they could share processor and so on and so forth. And you have the apps here. So 653 of standard software. Here we are warming up. The avionics applications communicate among themselves, communicate with each other by sending messages with communication ports. In AFDX, as a network layer, it has some ports that correspond to other ports at application level. So if you are developing a NOSI protocol, well, it perfectly fits, but it is highly related to the top layer and the bottom layer. There are two layers that share AFDX and ARINC 653. One of them, it's a sampling port, and sampling sends messages and replaces the previous one, so it always has the most updated version. And after that we have a queuing port that sends messages. There's another port in AFDX that is SIP, that is for interfaces between AFDX systems and non-AFDX systems. But this has, well, this we could leave this for other speech, okay, maybe for next year.
So think about a network card to connect to the AFDX switch. So in avionics there are different partitions, different applications. We have the sampling ports that are highly connected. There is a concept there that does not show anywhere. It is the concept of reliability. The application layer fully trusts the network layer. There is no authentication system between the two layers or domain ones. This is the way this architecture is structured. It's quite a simple structure. Very quickly, well, I will try not to bore you. This AFDX concept is important. Ethernet is the half duplex. We all know it works, performs all right. We are all aware of it. But you also know that there may be collisions in terms of packet delays, and this is unacceptable in avionics. And that's why AFDX was created, which is the half duplex. And it has been thought for critical systems such as engines, flight systems. So at the end of the day, we have avionics systems connected to AFDX, and they are connected through a switch. A switch is a key part. Each avionic subsystem is directly connected to a switch over a full duplex link with one pair of to transmit and one pair to receive. I will go fast, only 30 minutes left. I will not repeat things that I mentioned before, but I'd like to share with you this overview. This is a highly profiled network. Configuration may change significantly depending on the parameters, the type of hardware, equipment, you name it. Configuration is very sensitive. We are talking about sensitive information. Full duplex, I mentioned that before. It is a switched network. It is a deterministic network. We want to ensure bandwidth. So the 429 was a point-to-point network. This one simulates a point-to-point network. It does that through virtual links instead of cables. Virtual links is a medium, very important to simulate point-to-point. And another important concept is redundancy. Here we will always have two networks, different networks, delivering the same information, and someone or something would manage the redundancy and would approve some packets and versus others. So this is an AFDX structure. So there is a payload of AFDX. It also has information about UDP, IP, and destination addresses, as well as origin addresses. Why point to point? Well, we are talking about 6 bytes. That's it. Virtual links is a way of routing packets in the network. Same as in an ordinary network, we route through an IP. This time we use a virtual link. We are talking about a 2-byte value, 16 bits, and it is used in the 16-byte value slot. All in all, each VL is a logic path from one ES system to destination ES. There is a limit, which is set at 4096, and the bandwidth is allocated to each virtual link. Some of them may be more of a priority than others, and this is a parameter that can be configured. There are very many other things. We also have some virtual links that are smaller, for which there is no dedicated or bandwidth. We want to guarantee a service, both in terms of latency and bandwidth. Here, no packet delivery is accepted. So this is curious information. The packet delivery may fail. So this is extremely important. This is BAG. It stands for bandwidth allocation gap, which is to say the time between packet delivery. So for correct delivery and for correct reception, we need to set the right back values. They range from 1 millisecond to 128 milliseconds. Very important parameter. There are other parameters. I'd like to mention jitter. This is small interval in the back, so that back is not as strict. Jitter depends on the underlying technology, and it also depends on how you want to process that well. Perhaps you want to set some internal delay in bags or not. With this, I mean that configuration is not just the value. There are other parameters in play, And well, operating this, if you are not aware of the configuration, may be challenging. Addressing 16 bits, as we said, in Airbus, we've been using 12. It is least significant, and most significant 4 bits are set to 0. So it's identification of the redundant network. I repeat, these are separate networks with physical cables, with physical cards. Everything is separated. All this is aimed at preventing failure. So the difference of safety and security. Safety, it's about likely failures, and security, we all know that security is about planned attacks. So critical areas in aircraft are redundant. The default mode is about transmitting the same frame with an identical frame sequence number. So destination, the first valid packet that is received is taken as good, and it is passed on to the application. If a different packet is received with the same sequence number, will be ruled out because there is a winning packet. What actually matters is the first packet. Pressurization system. I have a video to play. Well, I will just play it briefly in the interest of time. It's from Airbus A320. Well, A320, A340, 430 are not exactly the same, but are similar aircraft. system is quite simple. These are applications that are running in the cabin, and they use data from the network. They are user interface. In case of differential pressure, there are three important parameters. Well, in case of pressurization, there are three important parameters: the differential pressure, the difference between inside and outside, then the vertical speed, that is to say the vertical speed at which the cabin altitude is fluctuating, and then the altitude. It's the altitude above sea level. Well, as you can imagine, there is lots of significant engineering behind it and lots of people working. These are quite, this is basic information that I'd like to remind you of. So pressure will be zero on the ground and increases as the aircraft climbs. The normal position during the flight, when the lights are out, it's automatic mode. There is nothing to be done. Everything is set on automatic mode and everything works perfectly all right. In these conditions, under this condition, the pilot is not expected to do anything unless there is a problem, an alert, an incident, and if so, in that case, the pilot could switch to manual mode. There are two main status: on ground and in flight. Well, the software changes its behavior as well as the systems. How do we know whether we are on ground or in flight? There is no 1-0 signal. This is calculated or worked out based on signals that are coming from very many different networks, and many of those signals are AFDX signals. Now we go into Orphans 2017, very good album. I recommend it to you. First Valid Wins. As I was saying, in AFDX there are two networks. Packets are transmitted through both networks, and integrity is checked on each channel to check the packets that are valid and those that are not valid. Once that is done, there is a redundancy manager. So the first valid wins. So if we succeed to have a valid packet, that valid packet will become the winner. And someone may go and say, what happens if I disconnect one path, one channel, connect my equipment, and I start to do things? What are my chances? If our packet is valid, we win. That is our objective, because the packets coming from the other path are ruled out. But when we go into this high-profile network, let us say that we are talking about a gray box testing, meaning we really need to know the packets that we want to find, the information that we want to find and to change. But in this case, we don't know anything about the virtual link or configuration parameters or back value. When we go into the path into the channel, the other party will win, because their packets will win. So let us talk about primary and secondary channels. And we may think, what happens if I connect and disconnect the primary channel? Well, if I do that, I will keep it for myself. Yeah, you can do that, but perhaps you will not be having immediate good packets, and that generates a communication failing, and that translates into pilot and co-pilot detecting or seeing that communication failure. So what can we do the primary channel? How do we want it to be like? So all the packets has a previous sequence number. So the PSN is always stored and used for calculation of the next sequence number. All the packets that are duplicate or have an erroneous sequence number are discarded. There is another parameter which is known as Qmax. Qmax is the difference between the redundancy manager redundancy manager to rule out packets. If we send a packet in a time range below Qmax, we are highly likely for the packet to be considered as valid, even though we have to continue competing against the other channel. But if we go above Qmax, there will be a synchronization period. Let us say that both paths will be reset, and after the resetting, the first packet to arrive is the winner. And before finishing, I would like to say that this is real testing, this is public information, it is available on the internet, not only these screenshots, but also the videos that I showed you. So this content is content coming from lab tests, and actually for that we used only a couple of tools. Wireshark, you are all aware of it. If you remove one network cable, then you log into the switch. First of all, you really need to know which are the good VLs. Therefore, you need to know the packets you are looking for, and then on the monitor node, you will see on the screen which are the nodes, which are the teams that are being involved in this communication of messages, and then you will have the information or the packets that you want to get. Also, there will be packet capture, and then you will be able to tamper frames or the packets once you have captured them. KB, it's another well-known tool. It is a tool to inject frames in the network. It is very simple. It runs in Python. And then the packets that we have tampered can be injected with modifiable transmission rates or with any other parameter that we want to change. We use 4 techniques. These are not standard techniques. These are just methods that we felt are likely to be successful. So the first one is the skew. It changes the transmission ratio, increments of sequence number as offsets to the right. Then reset. The reset default packet that when transmitted resets the redundancy manager. That does not mean that every time I transmit a packet, the path will be resetted, or the redundancy manager will be reset. Another way to inject packets or to model packets is known as bag-inc, which is incremental sequence of bag to somehow reach out or overlap the other path with the same bag. Remember the jitter. Within the same bag, there is some lag defined by jitter. So you have to test that very quickly, because if there is a communication failure, that might be notified to the pilot or co-pilot. And then we have fast, which is about fastest incremental sequence. When you play around with this, sometimes it works, sometimes it does not work. And well, one of them, when performs well, is very, very successful. I'm not going to tell you which one that is, but if you do it with that successful one, you are very likely to manage easily what you want to do. Right, now I have 2 more minutes and I'll play a video. In flight, commercial flight. The previous video was done in France. This one was done in Spain. And track is from AFDX Twin. So now, imagine that we want to depressurize the cabin. We know that in flight status and in automatic mode, everything works perfectly all right. Nothing should happen. But what happens if ground status gets in as the aircraft is in flight? The in-flight status is detected based on different signals from various equipments. For safety reasons, signal values are promediated. Then there is also a voting process in place. If there are 3 systems and 2 systems issue the same voting, those 2 systems win the voting. So this calculation of this decision making is not easy. What is it needed? Physical connection. This is very important. You need to connect to a switch which is on board. It's a special switch. You need to have that physical access. We know that that could be a hindrance. Also, you need to detect specific virtual links. You also need to be able to usurpate the channel through some of the techniques that we've seen before. And once you've done that, you need to win the vote. Well, this is all from me. Thank you very much for your attention. And I hope I haven't bored you a lot. Any questions? Thank you very much for your presentation. Regarding your conclusions, what about the safety of those switches within the aircraft? Well, they are in the cabin. Some of them have switches, others are not in the cabin, but they do not have any switches. I'm talking about, for instance, USB connectors, and many critical equipment are in the inside the aircraft. And many of the systems have switches have a tampering system, but not all of them. It also depends a lot on the configuration. Well, first of all, physical security is that they are difficult to access. Connectors are difficult to have. Well, you don't have them, but you buy them on eBay. So this is physical security. In terms of logical security, there is no authentication system. If there were authentication system, connection system, you couldn't do that at all. And now, anything which is in flight is much less accessible than anything that is on ground. Well, I have a question, and do not feel forced to obliged to answer. If I could reach the switchboard of the aircraft, is the switchboard connected to both paths, and could I attempt to inject? What do you mean by the switchboard? Well, something that would manage a card or any other protocol where I could inject anything. Well, it depends on the equipment. You cannot do that with every single equipment. Actually, you could cancel redundancy, but often you don't cancel redundancy because you need redundancy. So this is kind